Well, good afternoon, everyone. My name is Howard Newkrug, Director of the Water Center at Penn, and we're going to wait a couple more minutes to make sure that everyone who wants to be on the line has made it into the show. So one more minute or so, and then we'll get started. Well, good afternoon, everyone. Again, I'm Howard Newkrug. I'm the founding director of the Water Center at the University of Pennsylvania. Welcome to the Penn Alumni Water Forum Speaker Series. Today, we'll be hearing about a major environmental improvement project happening along the Anacostia River in Washington, D.C. Today's presentation will be on D.C. Water's Clean Rivers Project, and more specifically, its newest link, the Northeast Boundary Tunnel, a 13-mile-long tunnel opening almost any day now. Thank you to our partners who helped put this event together, the Penn Club of DC, thank you very much, Penn Alumni Water Forum, and of course, DC Water. Next slide. Yes, brown is sexy because it is green, and the water industry is moving forward with doing different things than we used to do with wastewater, and because of that, that's why you're seeing things like the Anacostia River cleanup project happening. In fact, it's so sexy that we're reinventing wastewater as a renewable energy source, as a carbon sink, a fertilizer, and it's being reused and reintroduced as pure drinking water. Next slide. Our motto at the Water Center at the University of Pennsylvania is community, equity, science, resilience, and justice. Our work is founded on the principles that clean, accessible, affordable water is a human right, and we support communities in meeting their critical water challenges by identifying resilient and sustainable solutions based on equitable principles that reflect community voices. And we support the development of future water leaders. We call them next-gen water leaders within these communities and within the larger water sector, so that this water decision makers reflect the progressive values of the water industry and the communities that they serve. Next slide. Our core themes at the Water Center are equity, resilience, climate change, water leadership, and water innovation. And we do this through a number of mechanisms. One is, of course, research. Mostly what we do is applied research and policy, networking, engagement, and empowering. Next slide. I'd like to introduce our speakers today and talk again. The topic is DC Water Clean Rivers Project, and we're very, very fortunate to have Gordon Evans here with us today, and he is a registered professional engineer who has served as a private sector consultant on numerous water and wastewater collection, treatment, and conveyance projects in multiple states. He's worked as a public works construction contractor, building water and wastewater treatment and conveyance systems. Since 2013, government has been lucky enough to have Gordon join the public sector as an employee of DC Water and Sewer Authority in Washington, D.C., serving as the program manager, tunnel design for DC Water's Clean Rivers projects. We have two moderators today, and both are from the Penn Alumni Club of DC. First moderator is John Moyer. He's the vice president, Highland Avenue Partners, and he holds a BS degree in chemical engineering from this great university called the University of Pennsylvania, and also holds engineering and finance degrees from Villanova and Penn State. He has served as an executive board member of the Penn Club of DC for 3 years, currently serving as club secretary. John leads management consulting organizations focusing on operations, mergers and acquisitions, and supply chains for the food industry. The Board of Supervisors appointed John to the Loudoun County Water Resources Technical Advisory Committee. Our second moderator is Vivian Ramirez, who is the development manager for Seneca Group and is the president of the Penn Alumni Club of DC. Vivian is a 1996 graduate of the college with a Bachelor of Arts in Design in the Environment, and a 2019 Georgetown University graduate with a Master of Professional Studies in Real Estate Finance. She has been in the DC region's real estate industry for over 25 years with multiple sector experience. She most recently delivered the Amazon headquarters HQ2 development in Arlington with her Seneca Group team and as a planning commissioner with the city of Alexandria. So welcome everybody. I'm going to turn this over to our moderators now, John and Vivian, and to get Gordon ready to give his presentation.
Fantastic. Howard, thank you so much for the
Sure.
wonderful introduction. We are very excited to be joining you all today in this webinar, hoping that this will be very informative for all of you. I will definitely put a quick little plug out there for the Penn Club of DC. I would say, as all of our alumni clubs do, serve as beacons for all of our graduating Quakers. Wherever you are in the world, there is always a club to be able to serve you and to be able to connect you all. I know that for one, wherever I go to travel, I usually check in to see what the local Penn Club is doing, and it's a great way to be able to connect with fellow alumni. In our area, in the DC region, we do a lot of events, a lot of opportunities for our alumni to be able to engage with one another and connect. If any of you here are in the DC region, you know that it's a fairly transitory area, so these kind of common threads to be able to bring us together are ever more important. With that, I don't see Gordon with his video on just yet, but I think we are ready to turn it over to Gordon, and there he is. Excellent. And Gordon, there you are. And we are looking forward to your presentation today on the Clean Rivers project.
Thank you, Vivian. Are you able to see the slide number 1 with the big TDM? Excellent. Okay, so thank you, Joanne, Vivian, Howard, and Emma behind the scenes for the excellent introduction. What you're looking at here is a tunnel boring machine. That's going to be the kind of the centerpiece of this talk today. And what I'm going to be talking about is the DC Clean Rivers project, and specifically the Northeast Boundary Tunnel. And my name is down here at the bottom of this slide, Gordon Evans, Program Manager, Tunnel Design, DC Clean Rivers Project. So as I alluded to, what we're looking at is a TBM, a tunnel boring machine. It is gigantic in size. It is about 26 feet in outside diameter. And at the bottom left of this photo, you can see a little green man standing there by a green column. So that gives you an idea of the size of this tunnel boring machine. It is, as I said, about 26 feet in outside diameter. It is about 1 football field long, so you can't see the end of this. It is so long. It has cutter devices, cutter wheels and blades on the face of it that you can see. Those are the ones that cut through the sand, gravel, and boulders. And then it has voids in the cutter wheel. That's where all the spoil falls. It enters in there. It goes to a screw inside the TBM that then conveys this soil to a conveyor belt. The conveyor belt then transports this spoil 1,000, 2,000, 3,000 feet back to the beginning of the opening where it's removed. This tunnel boring machine operates very deep in the ground, 100 feet down, 50 to 120 feet down. The pressure at that depth is going to be 1, 2, 3, 4 bar. Each bar represents an atmosphere. And so when this TBM is operating, it's operating under probably several atmospheres. The cutter head that you're looking at has to be maintained. Those blades get dull after a while. So crews have to enter this area and replace those blades sometimes. That means they have to enter a pressurized atmosphere that that is kind of like a scuba diver going down to a 50 or 100-foot depth in water. So a scuba diver, when he enters a pressurized area like that, has to decompress, come up slowly, or that sort of thing. And for that reason, this TBM includes behind it a hyperbolic chamber, and that is the chamber in which the personnel would enter so they can reacclimate to atmospheric pressure. Okay, we'll go to the next slide. And the, let's see. Okay, here we are. Slide number 2. This is the agenda that we're going to be talking about today. We'll go through an overview, status, performance, and then talk about specifics of the Northeast Boundary Tunnel. And then we'll have about 15 minutes for questions at the tail end. And what you're looking at is another one of the tunnel boring machines that was used during another stretch of the project. The system we're looking at is called a combined sewer system. And what we're looking at on the left is a map of DC. It's kind of rectangular in shape. It has 2 rivers shown on it. The river on the left is the Potomac River. The smaller river on the right is the Anacostia River. And then a very small blue thread down through the center is Rock Creek. And this view shows us the area in green, which is the 1/3 portion of DC that has combined sewers. That's an old style sewer, but that's exactly where the problem is that we're having to address here, because these combined sewers have overflows into these waterways, and these overflows carry untreated wastewater during wet weather events. So these are all being addressed in this project. We know there are about 48 of those overflow points in DC, and we're going to try to mitigate all of them as their flow goes into these 3 receiving waters. This slide shows an illustration of the conditions on the Anacostia River before we started putting a CSO tunnel along the Anacostia. On the bottom, on the right side, you see one photograph that is a CSO discharge. That's a combined sewer overflow discharge to the Anacostia River. This is during a wet weather event. And down below is an example of trash on the Anacostia River. That's floating trash. That might be bottles, cans, anything that gets swept into the storm system and gathers here. And so I'm going to guess that I think we've got maybe 88 people signed on here. If all those 88 people, if you could all look back on your experiences, I'm sure all of you at one time or another have used a garbage bag and cleaned up debris on the side of a river. And so imagine yourselves, all 88 of you, cleaning up this amount of debris that is shown here, and it's quite a large volume. And if you filled up all your garbage bags, that might be 100 or 200 pounds of floating debris that you would get in your garbage bags, and you would save it from going down the Anacostia into the Chesapeake Bay. The reason I'm pointing this out is to compare it to another gathering of this kind of floatable debris later, an automatic method that we've got. We'll talk about that later. The upper left side of this slide shows 2 examples of combined sewer systems. The upper left is a sewer system during dry conditions, and the sewage is shown in brown, going its normal path out of a building into a sewer, and then being diverted to the Blue Plains wastewater treatment plant. That's normal flow during dry conditions. On the right side, imagine that same area with rain coming through. Rain enters this system and dilutes the sewage. It has become so voluminous that then under normal times, it has no option but to overflow into the river. That's what creates a problem here, because that's untreated sewage that goes on in the river. That's what we're trying to remediate here. And then down at the bottom, the bullet here, prior to the Clean Rivers project, we had 2.1 billion gallons of untreated sewage and runoff going into the Anacostia River, a huge amount. Okay, we'll move to that's slide 4. We're going to move to slide 5. so these are some examples of flooding that were recorded. Many of these are along Rhode Island Avenue, a very old and busy and important thoroughfare through DC. And you can see that we've had severe flooding, street flooding in that area, so much that some of these cars are nearly half covered. And so this is part of what's going to happen, part of the situation that will be alleviated by this tunnel system. But again, Rhode Island Avenue, we're going to look at a map of where this is located and what's happening to try to mitigate this. Okay, moving on to slide 6. And here we've got another map of the district shown in the right. It's another rectangle, and it has, again, on the left, the Potomac River. That's the big blue line on the left. On the right side is the tributary of the Anacostia River, and along these rivers right now are an orange line, a purple line, and a yellow line. The purple line is a portion of the sewer that has been in place since 2018. It's called the Anacostia River Tunnel. The orange line is the Northeast Boundary Tunnel. That's the portion that is just about ready to go online. We'll be talking about that specifically later. And then on the left side, the yellow line is the Potomac River Tunnel. That's the one that construction hasn't started yet, but it's coming. So these are the 3 main objects of our program here. Also on that same map is in the upper center is a bright yellow area with orange spots. That's the areas where green infrastructure is being used to mitigate some of the excess stormwater flow. That's not going to be the focus of this presentation. We're looking at tunneling only, but that is an important component of dealing with stormwater runoff here in DC. Then the big bullet on the upper left is mention of the federal consent decree with the APA, the United States Department of Justice, the District of Columbia, and the District of Columbia Water and Sewer Authority, or DC Water. So some of you are going to be familiar with that term, a consent decree. Those exist across the nation, but that's kind of the lever that is used to encourage communities to install systems such as this over a certain period of time. And so we'll talk about that a bit more. These bullet points down here in the bottom left give you an overview of how big this project is. DC Clean Rivers project is $2.99 billion. There's a portion called nitrogen removal that is $950 million. The total of all this is about $3.9 billion. The time that this consent decree allows us to implement this is 25 years. So we started back in 2005, and we've got until 2030 to get it finished. And I'm going to anticipate one of the questions that I hope somebody in the audience asks: is this project on time, and is it within budget? The answer to both of those is yes. It looks like we are going to meet this timetable, and it looks like we're going to stay within this budget. And remember, this is being constructed in Washington, that has maybe a reputation for the other direction, but our project is going to be on time and under budget. We're also looking forward to a 96% reduction in combined sewer overflows and flood relief, and then approximately 1 million pounds per year of nitrogen removal. Looking at slide 7, this is maybe a type of drawing you may have never seen before. This is a profile of ground. The tan color is the ground surface. It goes up, it goes down, and then down below is a depiction, a cross-sectional view of our tunnel. The portion on the left is colored in purple. That's the portion that it has been in service since about 2018, and the portion on the right is in a tan color, and it is the next segment that's going to go in service in 2023. You can see that there's a slope in this tunnel from right to left, and that's by design. When tunneling engineers, sewer engineers put these in place, they try to get a certain slope, which then renders a certain flow velocity. As the flow goes through here, that flow velocity, if it's high enough, will pick up all the debris in the invert of the sewer and carry it to the plant. So that's a kind of a self-cleaning mechanism that the engineers try to design into this. Also in this this profile are two dotted lines, one kind of in the center, and that's one dotted line that depicts 157 million gallons of storage. That's the requirement of the consent decree. And as soon as we get Northeast Boundary Tunnel online, we will achieve that. Above that line is a second line. It represents almost 200 million gallons of storage. And after this is all finished, that's kind of bonus capacity we feel we'll have in place. So we will have well more volume stored than we were obligated to have in the consent decree. Okay, moving to the next slide, which is slide 8. This is a slide kind of colorful with a graph in red and green colors, and what each one depicts is the amount of flow that our tunnel system saw in these various years. And in 2018, that's when let's see. That's the first flow that our installed tunnel system saw. We got a huge amount of flow. That bar graph is up to 60.1 inches. That's way more rainfall than was expected. And then the red and green colors depict the green portion is the portion that was captured by the tunnel, but it was more flow than the tunnel could handle, so it overflowed, and that's what the red portion is. But you can see a minority of flow did overflow, and that was the case in every one of these years, 18, 19, 20, 21, 22, 23. The majority of the flow is being captured in the tunnel system, and a minority of it is being discharged untreated in overflow. And then the bullet points on the left, these get to something we were talking about before. The first bullet over, 15 billion gallons of combined sewage has been captured between March 2018 to July 2023, a huge amount. Now the second bullet here, this relates to what we were talking about in the beginning. If all 88 of us were out with our garbage bags cleaning up trash along the river, we might gather 200 pounds of debris. Well, compare that to this number you're looking at here. This tunnel system, since it's gone online, has captured over 9,800 tons of trash. There's a debris and other solids. There's an automatic mechanism that's built into this tunnel that captures those bottles, those cans, screens them out, and then puts them into dump trucks, and they go to landfill. So they do not go to the Potomac River. They do not go to Chesapeake Bay. They do not go to the Atlantic Ocean. They get captured here. And there's a benefit to that. Because that's made residents in DC happy, because the Anacostia River is actually visibly cleaner. In fact, the rowing coaches in the Anacostia at the local high school have said that they used to have to cancel rowing class whenever there was a big rain event because there's so much trash on top of the Anacostia. They don't have to do that now because much of this trash gets intercepted and gets sent to the wastewater plant for disposal. And then finally, the last bullet point, 92% capture is what we've achieved, exceeding the 80% predicted capture at this stage of the event. Okay. All right, moving on to the next one, slide 9. Here's another map, this time of the Northeast Boundary Tunnel. That's what we're going to talk about specifically. The blue body of water on the right is the Anacostia River, and and the portion that's along here is about where RFK Stadium is. If any of you kind of remember where along the Anacostia that is. And this brown line here is the path of the Northeast Boundary Tunnel, and the upper portion of it, the diagonal portion, it parallels Rhode Island Avenue. Remember, we saw those photographs of flooding along Rhode Island Avenue. Each one of these red dots or circles represents a diversion structure, and that enables the surface water to be diverted into this very deep tunnel system, might be 50 to 120 feet below the ground, and gets it off the streets. That's the whole purpose of this tunnel system. So you can see we've got several of these diversion facilities along, especially Rhode Island Avenue, and then other places. Down in the bottom left is a small detail of what a diversion structure looks like. We'll look at a bigger version of it later, but in essence, it's got the tunnel, which is down below 100 feet below the ground, and then above on the surface is the diversion structure that sits astraddle an existing sewer, and whenever that sewer gets too full, the flow is diverted and drops down a shaft and goes into that tunnel system. Regarding the bullet points on the right, the essential purpose of this is to increase the capacity of the sewer system, mitigating flooding and improving water quality. Now, that word mitigating is there on purpose. That means it lessens the severity of it. It does not mean it eliminates it. We cannot do that. The best we can do is mitigate it, make it much better than it was before. But that's a deliberate word there that I'm trying to convey the meaning of. The second bullet point, this northeast boundary tunnel is about 27,000 feet long, 23 feet in inside diameter, and ranges from 50 feet to 160 feet below ground. These, as we talked about, these facilities are constructed near chronic flood areas. There's also a ventilation control facility to vent the system. We'll talk about that a bit later. But when you in a rapid manner fill up this tunnel with a lot of flow, the air in it has to go someplace. So there's going to be a ventilation facility at various places to control the exhaust of that air as the tunnel fills up. And then finally, the captured flow is delivered to Blue Plains Advanced Wastewater Treatment for treatment. And the construction is 2018 to 2023. Okay, moving to slide number 10. This is a typical construction site. And in the bottom right-hand corner, you can see how crowded it is trying to build anything inside crowded DC. So this contractor has a triangular shape here. He's crammed everything possible into it. And then after construction, you can see the depictions on the upper right of what this site will look like when he's finished. It will be a very welcoming park setting, and so the people in the community will probably have no idea what's down below, but they'll appreciate this triangular park they've got. On the left side is a plan view of a typical facility. You can see the aqua colored sewer coming in from the upper right. It intersects a circle in the middle of the site. That circle is the shaft that may be 50 to 120 feet deep, hits the shaft, and then adjacent to this structure is the diversion facility. That's the rectangular feature on the bottom. It sits astraddle the green sewer line. And then at the hypotenuse of this triangle is the ventilation control facility. That's the one that lets the air exhaust out of the sewer as it's filling up. Okay, moving to slide 11. Here you see a more detail of a typical diversion facility. You see the tunnel down below, and then up above, you see the diversion facility sitting over the top of a sewer. And whenever the sewer gets full, the flow is diverted down a shaft and into that tunnel. On the right side, you can see two details of what one of these structures looks like during dry weather. The flow goes straight through the green arrows there. And then during wet weather, the flow gets so much that it fills up and it crosses this red line here, which is a weir, and that's kind of the boundary into the next facility. On this slide 12 is a slide that deals with probability. This graph here over on the right is labeled flood relief, and each one of these columns here represents a type of wet weather event. And the first one is a 1-year event, then 2-year, and then 5-year, 10-year, 15, 20, etc. So the frequency of these storms varies. It diminishes as you move from left to right. So designers, when they design a stormwater project, have to pick a point that does give the community some relief, but the community can also afford. So the level of protection that the designers chose here is about a 15-year storm. So you can expect a pretty good amount of protection up to storms that have a frequency of about 15 years, but storms that occur every 25, 50, or 100 years, you're going to get some relief, but you're going to have flooding, guaranteed some flooding. So this is the decision that designers make when they are designing a system like this. And also this first bullet point on the left is the essential one. This is what happens. This mitigates the frequency, magnitude, and duration of sewer flooding. And then all these other benefits derived from that. Down at the bottom are some points. 1996, this is the volume of the flow that went out to the river when there were no features to block it. 2,142 million gallons a day. That's 2.1 billion per year, excuse me. And then all the way down to 2023, when the Northeast Boundary Tunnel is online, and will drop down to about 54 million gallons per year, a huge decrease in the flow. So we're to the point of questions. So start thinking about some questions. The photographs here on the left are really important to the people who put these tunnels underground. They tend to work 2, 3 or more years on this. They get to know each other, and they're working sometimes 1, sometimes 2 shifts. They get well and sick together. They have very few injuries, as it turns out. Safety is emphasized very highly on this project. So we have very few injuries, but here are 2 of the crews on the left. Down in the center, here's a picture of a tunnel boring machine, the cutter head at the bottom of the shaft, and very deep shaft. It seems like so far up to the air there. And in the right side, this is the construction of one of these shafts. And this is when it's flooded down at the bottom. Before the bottom has been sealed, they'll have to pump out this groundwater, put in a watertight seal to bottom, and that's how you construct one of these shafts. Okay, so we've gotten this done inside our 25 minutes, and now we're hopeful. We've got about 15 minutes for questions, so we're hope you all are thinking of some questions. Okay,
thanks.
John and Vivian.
Thanks, Gordon. Great presentation. Let's put the questions into the Q&A. They're already coming in. One question for you, just to understand a few things about project management at this scale. I mean, we've all been, or a lot of us have been involved in construction projects, but nothing in the $3 billion range. I'd probably just give us an idea how many. What kind of human resources are involved? I mean, how many people, what kind of disciplines? I can imagine all kinds of engineers, construction and operations. What's the kind of the scale of the people that are, been working on this thing?
Well, John, it's a small army of people, and they start 2 or 3 years before the actual construction begins. And some of the most important people at the beginning are specialists who are kind of a subset of civil engineers. That'd be called geotech engineers. And once a route is selected, they will do borings along the entire 27,000 feet of a sewer route, the tunnel route, and they'll make reports on what is down below, how deep the water is, if there's rock, if there's sand and gravel. So that's one of the big components. So that's the geotech engineers, and then other engineers do other components of it, and put a design together. The way we bid these is design build. So we put out a partially designed project, and then these tunneling contractors are competent enough. They know how to tweak the design and give us our maximum value for our dollars. But it's quite a few people, John.
Okay, and then another question that's coming in was about safety, and you obviously safety is extremely important in construction industry, particularly in tunneling. Gordon, what kind of things have been done recently to new procedures or new protocols to ensure safety, and how has the safety record improved on these types of projects over the years?
Sure, John. Well, let's go back a century or half a century or something, and compare what tunneling used to be like, it used to be a very dangerous thing to do. They would have maybe a fatality per mile. But as you've alluded to, safety has become much better these days. And part of it is the culture of it. And even for those of you who might have done some construction work in the past, even since your youth to now, safety methods have improved a lot, to the point that every one of our construction meetings starts out with a safety moment. We talk about all the near misses that might have happened, some of the injuries that might have happened, and okay, how do we prevent that from happening in the future? And projects will actually just come to a complete stop if there has been an unsafe act committed. And the safety manager has that ability. He can go directly to the president of the company and say, stop the job. You've got an unsafe condition here. But I'm glad somebody asked about that. The tunneling is much safer than it was a half a century ago. And that's because it's attended to so carefully every day.
Okay, thank you. There was a reference in here to nitrogen removal, and I think it said a million pounds, if I remember correctly. Gordon, can you help us to understand that? We're used to thinking about carbon balances, but what is that? What does a million pounds of nitrogen removal mean, and how does that happen, and where does the nitrogen end up instead?
Well, the nitrogen refers to a nutrient that is going to be a part of wastewater and farm runoff, and that's always something that wastewater plants have to get rid of. It's nitrogen removal is a part of every plant permit, and the reason you have to get it out of the environment and sequestered someplace is because it will, if left in the environment, it will induce growth that you don't really want. Like down in Florida, you heard those stories about big dumps of pollutants have gone into either the Gulf side or the Atlantic side, and they induce big blooms of algae. That's what nitrogen can do. So you have to grab that nitrogen where you can. That's going to be at the wastewater plant, and they can deal with that properly. But you don't want that going out into the environment. And you're right, nitrogen is all around us, and it's great. We've got to have it to grow our crops, but we don't want it growing algae where we don't want it.
If I could, I'll chime in with one of the questions here. What can we learn from this project to inform future projects like this for other jurisdictions? And were there green measures or green approaches, particular technological advances that you think helped to bring success to this project that other jurisdictions can learn from?
Sure, and in fact, what you're looking at is a sampling of a technology that's being used in many communities across the United States. Just go to Chicago. They've got a similar CSO system there. It's actually much bigger than DC's, and they've figured out that they and DC Water have figured out this is the most cost-effective way of dealing with huge volume of stormwater that you do not want running untreated into your water. So this is kind of a tried and true technique of building these tunnels now. They're called CSO tunnels. And then regarding the green infrastructure portion, you certainly can complement this tunnel conveyance system with green infrastructure, which, as we showed on one of our maps here, that's actually part of this program in one portion of DC, where they're using biofilters and various things like that to capture that runoff and deal with it before it runs off. So yeah, they're both quite valid means of doing it. They're just different means of doing it. And I happen to join the company in the area that deals with the tunneling side. Others specialize in the green infrastructure but that clearly is a part of our scope here. It's also part of our consent decree too. Thank you for that question, Vivian.
Yeah, just to follow up on that, there's a question in the Q&A, and please keep sending them in. And to follow up on what other cities can learn from this, there's a question in here specific to Philadelphia. Why was a similar tunnel water diversion and storage approach not taken, I guess, in Philadelphia? And that might be a question for Howard, or I don't know if you know the answer, Gordon.
No, and I wouldn't want to stick my nose into that because I just don't know that much about Philadelphia. I have to rely on the local engineers who examined the options, probably chose the best one for Philadelphia. I just can't say, but for DC and for Chicago, this was the best option to take.
I'm thrilled to help answer that question a little bit. And Philadelphia system is a lot larger than DC's system, and there is tunnels being built now under design and will be constructed. But Philadelphia has relied a lot more on upgrading its wastewater plants so that they can handle more flow. And they're also looking at, and also a very large 10,000 acre area for green infrastructure and many other little pieces. So it's comparable and it's long-term and the job will get done, but it's very, very costly. And we were very much limited by how much money consumers had to pay for these systems for Philadelphia.
Okay, thank you. There's a technical question in here as well. They're asking about the stormwater is diverted to the tunnel. Will it be eventually treated? In other words, is a tunnel providing temporary storage capacity? I guess is that the way to think about it?
Yes, that's exactly the way to think about it. There's another term that's used in wastewater. It's called equalization basin, and that's this technique of simply storing a flow and until you've got time to handle it later. And that's essentially what this giant system serves as, an equalization basin. And then according to the conditions in DC's treatment permit, the tunnel has to be emptied within a certain number of hours after each event. So that means that though a huge flow may go into the tunnel, then it can be pumped out at a certain measured rate. It goes through a treatment process, one of two treatment paths. There's a kind of an accelerated path and then a longer path, but really every gallon that gets down to the plant gets treated. And so it's just vastly better than the old system of sending all that flow out untreated. Did that answer your question, Howard? Or John, I guess that
Yes,
your question.
yeah, it was absolutely. The other question here is when you look at DC, and I don't know the neighborhoods necessarily. I live in Virginia, but is there differential benefits, or are there certain communities or certain neighborhoods that will see an immediate or a more significant benefit from a project like this?
Yes, John, there will be, and the specific one, I guess the two that will see the benefits right away are that Rhode Island Avenue area that we saw all the flooding on. But the second one is the Anacostia River. And it's really a shame that for a century, probably longer than that, the Anacostia River was used as just a trash dump for both industry and military. And so it became pretty polluted. So that was the appropriate place to start to clean up. Now river cleanup started before we started this project, but it's continuing. And all the people on both sides of the Anacostia are immediate beneficiaries of this, not just the rowing clubs, but the people who like to picnic along the side of the Anacostia River. That's possible now, and you just don't see all the trash along the riverbank that you used to. So we make presentations similar to this one to groups out in the 7th Ward, 8th Ward, and explain to them what we're doing. And boy, I just can't tell you how much positive support there is in the community. And these are people that are having to pay for it too. This isn't, of course, free. This has been financed with a 100-year bond And that's not a happenstance number. We are designing this tunnel so it lasts 100 years. So that matches the term of these century bonds, they call them. So the community is willingly paying for this, and I think they feel they're getting their money's worth.
Maybe I'll jump in with a little connected question here from a couple of folks. It sounds like there are some questions regarding kind of green mitigation approaches, right, for rain gardens, bioswales, and green roofs, sidewalk infiltration areas. Is there any consideration as well for that kind of primary treatment as being part of this overall program? I assume, as with typical infrastructure, a lot of these kinds of methods are provided on private properties as a means of pre-treating some stormwater before it hits the jurisdictional infrastructure systems. But as part of this DC Water Clean Rivers project, was there consideration for these kinds of green approaches as part of the overall system?
Yes, Vivian, that's a definite yes. In fact, some of the structures we've constructed have green roofs on the roof. So there's a good growth of plants there that get watered and maintained, and so that's a portion that's there. Then also in the parking lot, one of these facilities, all the runoff from the parking lot doesn't go just down to the storm system. It goes into a storage tank that gradually lets it out. Then also back to the map that we looked at earlier, we saw a portion of the city where there are specifically green infrastructure projects that are underway right now, and they include exactly the features you mentioned: bioswales and rain gardens. And let's see, I think on slide 6 we saw the portion of DC. It was in bright yellow with some orange in it, and that is where many of these green infrastructure projects are under construction right now. So yes, this has been a portion of this project. In fact, it is specifically written into the consent decree. So this consent decree that DC has doesn't just require the tunnels to be built. It also requires a certain number of acreage of these bioswales and things like that. There is a lot of alley runoff that has been covered with permeable pavers, so that flow doesn't just go to the storm sewer. Now it goes through these permeable pavers and may go into some kind of a storage tank down below, but it doesn't just go, zoom out to the Anacostia or Potomac River like it used to. It's being captured and benefited from because there are these bioswales that have been constructed in DC.
Fantastic, thank you.
Mm-hmm.
There's a question here about the design basis, and they're asking about the concept of the 15-year storm, which I think is, if I understood, was the design basis. So, which leads to, I guess, two follow-ups. One is why 15 years, I guess, and not something different. And secondly, maybe as a 15-year storm, what it used to be, or in other words, with, I don't know, if from more construction or maybe changes to climate and weather, are storms more severe than they used to be, and that will still result in flooding.
The 15-year was not an arbitrary number. It was something that you weighed the pros and cons of going with maybe 5 years, maybe going with 25 years, and the one that gave the most bang for the buck was the 15 years. That's why they designed around that. And the questioner is right that their 15-year storm isn't what it used to be, and we all know that there are increasing numbers of 15-year storms and 100-year storms that didn't used to occur so frequently, and that is true. But in order to construct this project that started decades ago, you have to start with a certain design point. That's the one they chose. And years later, it's turning out that was a wise decision, because the effect of it is very beneficial. This tunnel system is not overflowing excessively. It is doing its job. And then I have to repeat this point, that this tunnel system, as big as it is, will not bring relief for all events. The bigger events, it can mitigate somewhat, lessen the severity of it, but it can't completely prevent it. But 15 years has turned out to be a pretty good number to choose. It's vastly better than what it was before. So that's kind of the thought process they went through in selecting that 15. It was not at all arbitrary. It was carefully weighed. Both affordability were considered, and as well as function. How much relief can you give with that design? And that's the one they settled on.
Couple questions in here about the sort of the practical issues with tunneling. Can you, everybody loves big construction equipment. Can you give us an idea? Well, first of all, I guess is what were the dimensions, but secondly, of the tunnel, and secondly, how do they operate? I mean, do you tunnel from both ends? Do you tunnel a short segment, and then what's sort of the tunneling process, I guess, in making this happen?
Usually, in all the tunnels that we've constructed in DC, they've started at one point, and then they shoot for a destination downstream. That might be 5,000 feet or 20,000 feet. And amazingly, again, if any of you ever have done construction in the field, it would have been decades ago, but they used surveying techniques years ago and try to hit points on the surface of the ground as closely as they could. Well, surveying has advanced to the point that even underground, even 100 feet underground, these tunneling machines can be put on a direction, and thousands of feet away, they can hit a point within 3/4 of an inch. I know that sounds pretty remarkable, but it over and over again, they've proven that to be right. So they do have these automatic devices that keep the tunnel boring machine going in the right direction. If the tunnel machine gets kicked to the left or the right, up or down, it has to be corrected. And that can be done while it's moving along. But you can see it. They have the operator of the TBM right in the machine has a target on a screen, and he can see if he's staying on course, if he's going too far to the left, too far to the right, and make corrections. And of course, he has to turn every once in a while. That can be tricky every once in a while. You have these gigantic hydraulic jacks that force the tunnel to go in, turn right, turn left, etc. And that's a massive undertaking. But these machines are able to handle that and stay on course remarkably well.
Another question here: during the tunneling process, do you find any items of historical or archaeological interest that have been, or are you down too far for that sort of thing?
No, part of every tunnel is what they call a near surface structures. Every time a shaft intersects the surface, the DC rules require an archaeological survey be done, and then any features that are found, like old trolley tracks or things like that, then are recorded. And so you're right. In areas that are old like this, the first step is the archaeological study, and that might slow down the beginning of the job, but that's always done beforehand. But you're also right, getting down to depth, 20, 30, 40, 50, 100 feet down, you're not going to find that much down there that deep. But up toward the surface, that's where we find the archaeological artifacts, and they are recovered, recorded, photographed as a routine step of this construction.
Okay, Gordon, thank you. Those are the questions we have, and we'll you can continue to send them in. We'll get information for you later. So go ahead, back to the Water Center. I think you had some slides.
Hi, everybody. It's Howard Newkirk again, and just thank you so much, Gordon, John, Vivian, for this great presentation and questions and answers. And it's a fascinating project. And when someone asked before about Philadelphia and how Philadelphia and DC compare, trust us, we have been good friends and colleagues and competing on how we get to our final point and get the sewage out of the rivers. DC Water started a little bit earlier than Philadelphia, but we've been learning things from each other all along. So thank you all for attending, and have a very happy, for those of you at Penn, have a very happy Climate Week at Penn. And you can see here how you can get in touch with us. And if you have any more questions for Gordon or for the DC alumni group, you can send them through us, and we will make sure that they get to the right place. Thank you all for participating in this, and see you at the next seminar.